Welcome to another in the Dassault Systems webinar series on Dymola. I'm Michael Tiller, CEO of Exogeny Inc. I've been working with Modelica since 1999, and I've authored a number of books and papers on its use, primarily in the automotive industry. It's my pleasure to be working with Dassault Systems to create a number of 20-minute webinars that explain why I think the Modelica language and Dymola, the Modelica solution from Dassault Systems, provide such a compelling solution for modeling, simulating, and optimizing complex engineering systems. In this webinar, we'll give you an introduction to Dymola and its features. The first question you might have is, what is Dymola? Dymola is a model development environment. With Dymola, model developers can create individual component and subsystem models, and then assemble them into complete system-level models. These system models can then be used to predict the behavior of that system. In addition to being a model development environment, Dymola is also a simulation platform. Dymola can be used to not only create models, but also to simulate those models. Included in the Dymola simulation platform are post-processing capabilities to plot, analyze, and animate those models. This kind of upfront modeling and simulation allows users to explore their design space and confirm that their designs perform as expected without the need to build expensive physical prototypes. Dymola also supports collaboration through interoperability with other tools. For example, Dymola can export S functions that can be imported into Simulink. Dymola also supports the Functional Mockup Interface Standard, or FMI for short. FMI is a vendor-neutral format for model exchange and co-simulation that is rapidly being adopted by many tool vendors and industries. Dassault Systems fully supports the FMI standard. This means that Dymola can build and export functional mockup units, or FMUs, that can be used by over 50 other tools that support FMI. To understand some of the ways Dymola helps streamline the model development process, let's take a quick look at how models are built in Dymola. In many cases, models are built simply by dragging, dropping, and connecting component models to create schematic diagrams. When the system schematic starts getting too complicated, Dymola can help easily organize the system into subsystems. Dymola comes standard with a wide variety of different types of components from across many different engineering domains. In addition, a large number of specialized libraries are available for a wide range of applications, including vehicle dynamics, electric drive systems, air conditioning systems, and so on. But one of the things that makes Dymola so popular is that you aren't limited by what comes with Dymola. Unlike other systems, where you're given a fixed set of components to work with, Dymola is built on top of the Modelica modeling language. As we'll see, Modelica enables many of the advanced capabilities in Dymola. So what is Modelica? Modelica is a vendor-neutral modeling language used to describe the behavior of complex systems. Modelica is at the heart of Dymola's modeling environment. The first thing to know about Modelica is that it is multi-domain. Modelica was designed to support all domains of engineering, not just one. Dymola includes the Modelica Standard Library, a library of components from many different engineering domains, including mechanical, electrical, fluid, and thermal components. Dymola also provides a number of specialized libraries focused on a variety of engineering applications. Through the Modelica modeling language, users have the ability to build models of their complete system, not just one aspect of it. One of the things that makes Dymola such a productive model development environment is Modelica's support for different types of modeling. For example, Modelica supports Acausal modeling to capture physical behavior in reusable component models. Using Acausal modeling, users can create an electrical resistor model by using Ohm's law. But what makes Acausal modeling so important is the fact that users don't have to make one model that computes voltage based on current and another model that computes current based on voltage. Instead, they create a single model that captures the relationship between current and voltage. When the time comes to generate code, Dymola will use something called symbolic manipulation to figure out which form of Ohm's law is needed for each resistor component. Symbolic manipulation is used in many different ways by Dymola to streamline the model development process and improve simulation performance. We will discuss symbolic manipulation in greater detail later in this series. Now, having to make 2 resistor models instead of 1 might not sound like a big problem, but the problem gets worse when you consider a component like a planetary gear model. That's because for each connection to a planetary gear, the user might want to specify an angle, a speed, an acceleration, or a torque at that connection point. For even moderately simple components like a planetary gear, the number of different models you need to support all of these combinations quickly gets out of hand. When building models, it is important to use the right approach for each type of modeling. For example, one big advantage of Acausal modeling is that small changes in the system don't create a ripple effect through the rest of the system. To demonstrate this, imagine the following simple electrical circuit. Using a tool made primarily for control system design would mean creating a block diagram for this model. Taking this approach would require working out exactly how the equations in each component would have to be reformulated from this schematic form into a block diagram. Although this process of translating the schematic into a block diagram requires some work, the real problem comes when a small change is made to the model. For example, changing a voltage source into a current source. Because Modelica uses an Acausal approach for creating reusable component models that describe physical behavior, it is only necessary to change one component in this schematic, the voltage source, when using the Acausal approach. None of the other components are affected. On the other hand, using a tool that only supports block diagrams would mean reformulating the equations for all the different components. The result would be that one small change would lead to a considerable amount of rework. When using a tool that doesn't support Acausal modeling, the model development process is filled with lots of tedious, time-consuming, and error-prone work. This kind of approach is like being forced to do long division over and over again. These are exactly the kinds of processes you want to get out of your model development process. Dymola is like a calculator. It takes care of all the tedious, time-consuming, and error-prone work. This makes the modeling process faster, more robust, and it allows users to focus more on modeling and less on grunt work. As we've shown, Acausal modeling greatly improves the process of building models for physical components. But there is more to modeling systems than just the physical behavior. It's also important to incorporate control. This is why Modelica includes support for many different approaches to modeling. For example, if you are designing a control system in Modelica, then a block diagram approach would make sense. For this reason, the Modelica standard library includes a complete library of block diagram components for engineers designing control systems. In addition, Modelica includes support for other modeling approaches. For example, almost every product these days features some kind of embedded control system. For that reason, modeling the complete system also means being able to model the behavior of the embedded controller. Modelica includes advanced features for modeling sample time systems, state transition diagrams, and other essential features of embedded control systems. Speaking of embedded control, Dymola provides excellent support for integrating embedded control systems with physical models. Through FMI and Modelica's foreign function interface, it is possible to directly integrate control software into Modelica models for software-in-the-loop testing. Later in the development process, when embedded controllers are available in hardware, Modelica models can be exported as S functions and compiled using Simulink Coder. This allows high-fidelity plant models written in Modelica to be compiled and run on a wide variety of hardware-in-the-loop platforms. These models can then be used to support validation of embedded controllers. Earlier, we saw how Dymola allows users to organize their systems hierarchically into subsystems. Decomposing a system into subsystems doesn't just keep the schematics neat and organized. It actually supports a collaborative workflow and makes configuration management easier. For example, consider an engineering team working on a vehicle model. One group might be responsible for building engine models, while another is responsible for building transmission models. Modelica allows us to formally define the interface for both the engine and the transmission. By formally defining these interfaces, each team can work from this interface specification to design models that can then be easily integrated. But these same interfaces are also the cornerstone to improved configuration management. By formally defining interfaces for different subsystems, Dymola knows what models conform to what interfaces. That translates into a smoother experience for the user. Instead of hunting around for compatible models and then rewiring the schematic each time we want to consider a different subsystem model, Dymola's graphical configuration management features allow the user to effortlessly explore different design concepts or support varying levels of physical detail by simply selecting from a list of compatible models. Of course, building models is only half the story. The real insights come from simulating these models. Once a model has been created, Dymola can be used as a simulation platform with features for analyzing, plotting, and animating your models. Dymola includes extensive features for plotting and manipulating simulation results. When analyzing system response in the time domain, Dymola annotates plots with useful information like slope, as well as local minimum and maximum values. Dymola also provides an interface for understanding a system's frequency response. Dymola can linearize the system and use that information to create Bode plots or provide details on the poles and zeros for that system. Dymola also supports animation to help create compelling visuals. These animations not only provide the users with additional insights, they help non-experts understand and interpret the behavior of the system. Dassault Systems has pursued a strategy based on open standards. In doing so, we've created a model development environment that can leverage not just the rich capabilities of the Modelica standard library, but it has opened the door for customers to create their own high-quality content and combine it with a variety of commercial and open-source model libraries. Our customers have embraced this approach and published their results extensively. To see how Dymola has become a proven industrial solution, one only needs to look in the literature. Companies like Ford, General Motors, BMW, Daimler, Toyota, and others are all using Dymola. How can Dymola and Modelica help you? Dymola provides a refined model development environment and simulation platform for creating and simulating complex and complete system models. Built on the Modelica modeling language, users benefit from Modelica's Acausal approach to physical modeling, its multi-domain support, and its configuration management features. Dassault Systems is committed to the principle of openness. Dymola is an excellent example of this commitment. Through our support for Modelica and FMI, both of which are open standards, Dassault Systems has created a thriving ecosystem of capability and content for our customers while preserving the flexibility customers need to interoperate with as many tools as possible. Dymola provides proven industrial capability, specialized Modelica libraries, interoperability with other tools and platforms, and exceptional simulation performance. Dassault Systems have integrated Dymola's capabilities into our CATIA platform, so when customers are ready to integrate their Modelica models with their CAD design process, Dassault Systems will be there with complete support. We hope you have found this webinar useful. If so, you may wish to view the other webinars in this series. Thank you for your interest in Dymola. We look forward to hearing from you.